Yeah, someone's asking about the poll. Rita, the language poll. Do you have the numbers on that? Just pour avoir une idée.
There's still people answering. Perhaps,
Okay.
can everyone please answer the poll and then I'll close it. Okay. So here are the results.
Okay, great. Parfait. So the overwhelming majority are English. Il y en a quelques personnes ici, peut-être une personne avec une préférence francophone. Toutes les vidéos vont être présentées en anglais avec des sous-titres en français. Patricia est aussi bilingue, so we can take questions in both English and French, and all the videos will be in English. But if anybody else needs any clarification on anything, feel free to put any questions in the chat and we'll respond. So welcome everybody. My name is Adrian Kiva. I'm one of the members of the Pêche Coalition for a Green New Deal. I'm going to be our spokesperson today. There's a lot of other people too behind the scenes. So Rita will be hosting and Anita will be answering the Q&A. I think we have one more poll also.
Actually, we won't have the poll.
We're not going to use that one? Okay, great. So for those who don't know, the coalition is a grassroots group based in La Pêche and the surrounding areas advocating for rapid, inclusive, and transformative change based on scientific and indigenous knowledge, and advocating for a Green New Deal in Canada, or the paradigm of the Green New Deal, which demands a just transition with no one left behind. And mostly what we do is education. We also do advocacy at all political levels and work with local groups. So I'm just checking through. We're meeting virtually, but nonetheless, we are meeting and we're talking about political issues that pertain to this land where I am and where a lot of us are, which is unceded, unsurrendered Algonquin and Anishinaabe territory. We think it's an especially important thing to acknowledge in climate justice spaces because indigenous communities, indigenous peoples are often on the front lines of climate justice and are stopping the fossil fuel projects from being put in the ground. They have the knowledge for healthy relations among all life and the speakers today, so I'm just looking through my notes here. The speakers today, we're really excited to have with us Dr. William Muma, who is Professor Emeritus at the Fletcher School at Tufts University, and Patricia de Repentigny, who is a La Pêche resident currently residing in Boulder, Colorado, where she's about to defend her PhD thesis. Dr. Muma has spent 20 years identifying actions and technologies to slow climate change, and he was a lead author of 5 major intergovernmental panel on climate change reports, that's the IPCC reports. More recently, he has developed natural climate solutions that protect and restore forests and wetlands to remove more heat, trapping atmospheric carbon dioxide. Patricia de Repentigny specializes in Arctic sea ice, climate modeling, polar climate variability, and has done research on sea ice in the Arctic. She's the lead author of Patterns of Sea Ice Retreat in the Transition to a Seasonally Ice-Free Arctic, and co-author of many other scientific papers in the area. So the structure of this webinar today is we have some video clips, which we'll be sharing with you, which were prepared and shared with Greta Thunberg and the Dalai Lama. And we will be, just a heads up that we won't be sharing the video clips in their entirety. So there will be some, we will be ending some of them earlier. And if you want to see the full video clip, we will link that. And the reason that we're doing that is for time to give our speakers time to speak and respond to the clips, and also to have a discussion with them at the end, the Q&A. Okay. We're going to begin the evening with 2 film clips on permafrost and the Albedo Effect. And then Patricia de Repentigny will speak to her research in the Arctic. After that, we're going to show a short film clip on feedback loops in forests. And then Dr. Muma will speak. So throughout the presentation, feel free to use the chat function or the Q&A function. And then Anita will take your questions and give them to our experts. You can direct them to one or the other or to both. And I'm just checking my notes to make sure I'm not forgetting anything. Fantastic. Here's a short introduction of what climate feedback loops are. Thank you so much for being with us.
Earth is warming,
Rita,
caused by the burning of fossil fuels like oil, coal,
on the
and natural
PowerPoint
gas,
presentation, not on the,
filling the
not on
atmosphere with heat-trapping gas.
Technical difficulties. If
Sorry.
I could hum the girl from Ipanema, I would be humming the girl from Ipanema right now. Some waiting music.
Oh my goodness, sorry. Just give me a second here, sorry.
Yeah, no problem.
Okay. What were you saying, Adrian?
Well, I wish I had the tune for the girl from Ipanema, then I could entertain everybody. But I don't have very good pitch.
Are you saying there's no sound?
No, I was just making a bad joke. When you're ready, go ahead.
Oh, like, okay, so I thought I was sharing. Was I not sharing?
You were sharing, but you were sharing the PowerPoint, not the YouTube.
Okay.
There we go.
Like oil, coal, and natural gas, filling the atmosphere with heat-trapping gases like carbon dioxide, methane, nitrous oxide, at levels humans have never seen before. As the world debates how much more warming the planet can take, 1.5 degrees Celsius, 2 degrees Celsius, the climate crisis escalates.
The problems are that the world is becoming too hot for the present distribution of people, agriculture, human welfare, and human interest. And it's getting worse.
But it's more than our emissions heating the globe. Something else is at work here. The rising temperatures are setting in motion Earth's own natural warming mechanisms that then feed upon themselves. George Woodwell, a distinguished scientist and a lion of the environmental movement, has been sounding the alarm about them for the past 50 years. In a 1989 Scientific American article, he wrote that warming caused by human activity, rapid now, may become even more rapid as a result of the warming itself. 30 years later, climate activist Greta Thunberg repeated his warning, calling them irreversible chain reactions.
The popular idea of cutting our emissions in half in 10 years only gives us a 50% chance of staying below 1.5 degrees and the risk of setting off irreversible chain reactions beyond human control. 50% may be acceptable to you, but those numbers do not include tipping points, most feedback loops, additional warming hidden by toxic air pollution, or the aspects of equity and climate justice.
So what exactly are irreversible chain reactions? What scientists refer to as feedback loops.
A feedback that everybody is familiar with is an audio feedback, where if you put a microphone too close to a speaker, you get this terrible high-pitched screaming. And that happens because the sound comes out of the speaker and it goes back into the microphone. That's called a positive feedback because it amplifies the loop.
Instead of the guitar, emissions from fossil fuels are the input which add heat-trapping gases to the atmosphere, raising Earth's temperature and setting in motion self-perpetuating warming loops. Warming as a result of the warming itself. That ever-growing screeching noise is an apt analogy for the damage that human-caused feedback loops are wreaking on the planet. Scientists have identified dozens of feedback loops already in motion. It's imperative that we understand them if we're going to solve the climate crisis. As the climate warms, forests, once removers of carbon, release it back into the atmosphere as carbon dioxide, or CO2. Frozen ground in the northern hemisphere thaws and emits CO2 and methane. These are the kinds of feedback loops that lead to further warming, triggering the release of even more heat-trapping gases and raising the temperature even higher. In this series, we will highlight 4 of the major feedback loops impacting climate: the melting of sea ice in the Arctic Ocean, increased drought and fires in the world's forests, the decay of organic matter from permafrost thaw in the northern hemisphere, and disruptions to the jet stream and our global weather. Each amplifies warming, and combined, they are spinning out of control. If we take action now, we could slow, halt, or even reverse them before it's too late. If we don't, the planet will reach a tipping point where we will lose the world as we know it. And what does that tipping point look like?
A simple example of that would be if you push a ball up a hill, at some point you're going to get to the top of the hill and it's going to roll down the other side. There are some things like that in the climate system where it's really hard to get it back once it's rolled down to that other side and now it's sitting in a new valley.
With more than 7.5 billion people on Earth, a change this great would spell catastrophe. Humans are well suited to the world we've known. The sun's radiation passes through atmospheric gases, primarily oxygen and nitrogen, to the Earth's surface. Some radiation is absorbed by the planet and the rest would bounce back to space if it weren't for a tiny percentage of gases like carbon dioxide, methane, water vapor, and others that trap heat and warm the atmosphere. These heat-trapping greenhouse gases make up less than 1% of the total atmosphere, but they are essential in regulating the temperature. Without them, we would freeze, but too much of them would overheat the planet. Both are possible and have happened in Earth's geologic past.
So the kinds of things that keep climate scientists awake at night stem from their familiarity with the geological record that shows that the climate is capable of very abrupt changes. There are feedbacks operating in the climate system that may temporarily go out of control, if you will, and drive the climate to a different state. We cannot rule out that we may be in for such an abrupt change. So we don't fully understand them, but we worry about that a lot.
These radical changes include extreme temperature swings. During periods known as Snowball Earth, it got so cold the planet was covered completely in snow and ice. These alternated with hothouse climates, when virtually all the ice melted. Dinosaurs lived at the poles where forests and swamps flourished. These abrupt shifts were caused by complex global processes. This is the first time that humans have been responsible for an abrupt change. Today, Earth would naturally be in a cooling trend, but because of human activity, it's not.
We know from paleoproxy records that the Earth has been cooling for about 7,000 years. We recovered from the peak of the last ice age, which was about 22,000 years ago, went up, and it's been slowly cooling until about the time of the Industrial Revolution.
At that time, humans began emitting vast amounts of carbon dioxide. Since then, the atmospheric content of CO2 has gone from 280 parts per million to over 400 today, and could approach 800 by the end of the century. Of all the carbon dioxide humans emit each year, oceans absorb about 1/4. Plants take up another 1/4, and the other half stays in the atmosphere, accumulating over time and raising Earth's temperature. But the percentage nature removes is shrinking every year as forests are destroyed and oceans warm. Scientists estimate that doubling CO2 from pre-industrial levels could produce an increase in temperature of up to 8 degrees Fahrenheit. resulting in the deaths of millions of people and the loss of countless species. It's this human-caused warming that's kicking off Earth's natural feedback loops and heating up the planet further. National Medal of Science recipient Warren Washington, a groundbreaking climate pioneer, began creating computer models in the 1960s to predict the future of atmospheric warming and the role feedback loops play.
The question always was, how do we see the feedback mechanisms working realistically? We really don't know if we got the right amount of feedback in our models because they're so complicated in many cases. We had to do a lot of experimenting.
That experimenting, coupled with observations, paid off. Because of that groundwork, today's models have more accurately predicted what we're seeing today and what our future holds. This kind of research is crucial to understanding the policies we need to implement to avoid disaster going forward.
Climate policy really should be designed to avoid crossing the important thresholds, avoid crossing the important tipping points, and avoid setting off these important feedbacks. Because we need to essentially ask the question, how much warming is okay? Is 2 degrees okay? Is 1.5 degrees okay? We really don't know the answer to that very well.
And yet we continue to add more heat-trapping gases to the atmosphere, setting off irreversible chain reactions.
Where we are now is like driving in a car in a dense fog, and there's a cliff out there somewhere, but you don't know where. Do you want to be going 60 miles an hour, or you should be going about 10 miles an hour?
Today we have a choice. If we take our foot off the accelerator, stop deforestation, and regreen the Earth, we can reverse the feedback loops and begin to cool the planet.
And the solution is to make that transition away from fossil fuels and into a new green Earth. And it really does require a green Earth.
I'm encouraged by the fact that other countries have decarbonized their electricity sector in 10 to 12 years. So I know we can do it, and those countries that did it, by the way, grew their economies rapidly while doing it. But we have to put the incentives in place.
Even with meaningful incentives, it's going to take a while for the climate to recover.
Even if we stopped emitting carbon right now, it will take thousands of years for the system naturally to go back to what was before we started messing around with it. If we keep going industrially at the same rate we are now, we will have succeeded in roughly tripling the carbon dioxide content of the atmosphere over its pre-industrial value by the end of the century.
We have the technology and knowledge to solve the problem, to stop and reverse the feedback loops. But we need leaders who understand the urgency of getting it done, and an energized public to advocate for change. It's not going to be easy. We've let the problem go on too long.
That isn't to say, though, that we shouldn't do everything we can possibly do to slow down our emissions, because we'll make it that much better for our kids and grandkids in the future. The problems won't be quite as big. The warming won't be quite as strong.
The Earth will be just fine. We may take along with us, unfortunately, lots of different species, but there have been catastrophic extinctions of species in the past. I'm not worried about the planet, I'm worried about us.
Every great change throughout history has come from the people. We do not have to wait. We can start the change right now.
Problem go on too long.
That
We can start the change right now. We, the people.
Okay, thanks, Rita. Sorry, I hope that wasn't too abrupt for everybody. I don't enjoy watching those videos. before we go to the next one, which is albedo, just a quick technical question. Could people in the chat let us know if the bottom of the text, les sous-titres francophones, if they were clipped? Est-ce que vous pouviez les voir? Aussi, was it full screen? Text was clipped. Okay, thank you, Colin. And could you see was the video full screen, or was not showing full screen? Okay, so I was worried about both those things. Okay. So we will go to the next one. And if you should also be able to pin the video if we're not able to resolve that on our end. And I think when Rita, when you moved your mouse while the video was playing, that bumped the text up so I could read the whole thing. Yeah, the second line. So Rita, you might just have to, I don't know why it's doing that, but you might just have to kind of jiggle your mouse to keep the text high enough. Pour tout le monde. Okay, thanks for your patience, everybody, as we go through this. Yeah, Colin clicked to get it full screen. So everybody, you can click on the video and it'll go full screen for you. Okay, the second clip is albedo. Rita, whenever you're ready.
White puffy cumulus, dark nimbus storm clouds, wispy thin cirrus clouds. Not just beautiful to look at, clouds play an important role in Earth's climate. They're formed by water vapor, a naturally occurring gas created when water evaporates from lakes and oceans. Water vapor is also a heat-trapping gas. It's part of a dangerous feedback loop that's heating the Earth beyond its natural limits, accounting for about 60% of all global warming caused by heat-trapping gases in the atmosphere. As fossil fuel emissions raise temperatures, the atmosphere absorbs more water vapor, which then traps more heat, warming the planet further in an ever-amplifying loop. In fact, the water vapor feedback amplifies global warming from human activity between 2 and 3 times. For the past 30 years, Jennifer Francis has been studying how increased greenhouse gases affect the atmosphere.
Water vapor is just water in a gaseous form. When you take a pot of water and put it on your stove and boil it, you see steam, which is still in the liquid form, but then it disappears and it goes into the atmosphere and it's completely invisible. So the same kind of thing is happening in the climate system, where as we warm the air and we warm the oceans, more evaporation is occurring from the oceans and putting more water vapor in the atmosphere.
While some of this stays in the atmosphere and traps heat in gaseous form, some of it cools and condenses, forming clouds, which can both heat.
There we go. Sorry again, everybody. And I'll note that somebody else said that these subtitles were in English.
For tens of thousands of years, the delicate balance of Earth's climate has allowed human life on our planet to thrive. Today, that equilibrium is at risk as one of the most important cooling mechanisms, the Albedo Effect, or Earth's reflectivity, is threatened. At Earth's poles, snow and ice reflect up to 85% of the sun's rays away from the surface and back into space, helping to keep the planet from becoming too hot. But over the past few decades, this natural mirror has begun to break down as fossil fuel emissions raise temperatures, melt snow and ice cover, and reduce the planet's albedo. As the planet loses its ability to reflect sunlight, a dangerous warming feedback loop is triggered. The most alarming change is happening in the far north, where the temperature rise is causing the snow cover and sea ice to rapidly disappear. Don Perovich is a sea ice geophysicist at Dartmouth College. For the past 30 years, he's been documenting big changes in the Arctic.
There's always been this annual cycle. The ice grows, usually say for 9 or 10 months of the year, and then melts for a couple of months. What's changing now is the timing. The melting is starting earlier, the freezing is starting later. We have much less coverage every month of the year, particularly at the end of summer.
Global warming from human-caused emissions of heat-trapping gases, carbon dioxide, methane, nitrous oxide, and others, is increasing the temperature in the Arctic 2 to 3 times faster than the rest of the planet. Warming is then amplified by the loss of albedo as the reflective ice and snow disappear, exposing the dark ocean underneath.
Say it's April and we're flying above the Arctic and we look down at the sea ice cover. It's covered by snow. It's bright and it's white. Now, summer comes, that snow melts, you get more open ocean, you're absorbing much more heat. Instead of reflecting 85%, you're absorbing 90%. And so you're replacing one of the best natural reflectors, snow, with one of the worst, the open ocean.
Now, instead of reflecting the sunlight, the ocean absorbs it, heats up, and melts more ice, exposing more dark ocean, which absorbs more sunlight in an amplifying cycle.
As those darker waters warm, they emit carbon dioxide and water vapor, warming things further. So there are several aspects to this feedback in the Arctic problem which are truly frightening.
Scientists have been measuring Arctic sea ice since long before satellites began taking reliable measurements in the early 1970s. By the end of that decade, the climate models predicted sea ice would begin to disappear with the increase of heat-trapping gases in the atmosphere. Marika Holland is a climate modeler from the National Center for Atmospheric Research.
So our first climate models were developed in the 1970s. Those models, even in their simplicity, predicted that with rising greenhouse gases in the atmosphere, we would see dramatic sea ice loss in the Arctic, and the Arctic warming would be amplified relative to the globe.
And as measurement techniques improved, scientists were alarmed to discover just how much ice had been lost.
The volume has decreased by 75% in only 40 years. It's just a breathtaking change in a very short time. We call it the new Arctic now because it's so different from what it used to be. The ice now is mainly consisting of what we call first-year ice, which is just ice that's formed in that one winter, and most of it doesn't survive through the summer. It all melts.
Studies suggest that around a quarter of global warming is caused by the loss of this sea ice. But if you factor in the melting of snow cover on the surrounding land, together they account for an estimated 40% loss in the planet's reflectivity.
The snow cover over land is very bright and very reflective. It reflects an enormous amount of the sunlight away from the surface, just like the sea ice cover does. And we are seeing reductions in the aerial coverage of snow over the land, just like we're seeing reductions in the aerial coverage of sea ice.
With feedback loops amplifying the warming, the landscape of the Arctic will change irrevocably.
So our climate model projections suggest that we will lose the Arctic sea ice cover in the summer months altogether by the end of this century. If we continue to increase greenhouse gases in the atmosphere through the burning of fossil fuels, we ultimately will get to a state where we lose the winter sea ice as well.
A sobering prediction, considering that ice has covered the Arctic Ocean for more than 2.5 million years. And the warming happening in the Arctic isn't staying in the Arctic. The air there is mixing into the global atmosphere elsewhere on Earth and raising global temperatures.
The Arctic plays a very central role in Earth's climate. Even if you just lose sea ice cover in the Arctic, the tropics will feel that enhanced warming.
This means amplification of problems the climate crisis is already causing. Crops suffering, food prices going up, wet areas becoming wetter, dry areas becoming drier. And as the climate warms, it kicks in another feedback loop set in motion by the melting of massive glacial ice sheets. In the past 30 years, the loss of ice on the Greenland ice sheet has increased sixfold, leading to a rise in sea level. As the ocean rises, the higher, warmer water melts more land ice, raising sea levels further and melting even more ice in a vicious cycle. In the South Pole, the increased temperature is thawing the miles-thick Antarctic ice sheets that have been accumulating on land for over 40 million years.
Loss of ice over the Antarctic continent doesn't have as much of an albedo feedback because it's so thick. But as that ice enters the ocean, it causes sea level to rise.
If both Greenland and Antarctica's glacial ice shelves were to melt, sea levels would potentially rise by more than 100 feet. This resulting destruction to coastlines would uproot millions of people around the world. It would also mean the ice sheets would reach a tipping point, taking thousands of years to recover.
If we lose an enormous amount of ice from the land, reestablishing that is a very long timescale issue.
And if we continue with business as usual, the warming of the Arctic will cause the feedback loops at both poles to spin out of control.
The models predict if we continue on the path we're on, that the Arctic will experience very dramatic changes and that those changes will reverberate throughout the system, the human system, the biological system, the socioeconomic system.
With every country contributing to the problem, each now needs to be part of the solution.
That requires managing the world in such a way that we do not exploit carbon compounds and dump the waste into the atmosphere.
The emission of greenhouse gases is an example of a market failure. One business enterprise passing on the real cost of doing business to people who aren't party to that business. That is, most of the rest of us.
In every sector of the economy, we have the technology and knowledge to move toward sources of energy that do not produce heat-trapping gases. What we need is the will. We must stop adding fossil fuels to the atmosphere, which are warming the planet, melting the ice and snow cover, and lowering the reflectivity of the Arctic. If we cut emissions, stop deforestation, and regreen the Earth, we can slow, halt, or even reverse the feedback loop. Lower temperatures, regenerate snow and ice cover, increase reflectivity, and heal our planet.
You have all this heat in the ocean. It would take a few years of cold temperatures to get rid of it. But once you did, you would get ice to form again.
The most important thing citizens can do is to educate themselves on this issue and vote for politicians who take this problem seriously and have good ideas for how to solve it.
I'm optimistic by nature, and I become more optimistic when I see so many people that realize there's a problem. The pessimistic part of me says the longer we wait, the harder it gets. It's time to act.
Thanks, Rita. Patricia, je vous inviterai de suivre votre vidéo. Thanks also to Rita for doing this live troubleshooting of these technical problems we've been having. We did a dry run earlier, and this wasn't an issue. So we'll keep working on it while Patricia gives her presentation. Patricia, are you there? Okay, awesome. Okay, merci.
Okay, can you guys hear me?
Yeah, we can hear you.
Okay, great. Let me put that in presentation mode. Okay, so Hello, everyone. As Adrian said, my name is Patricia Doropansny. I'm a PhD candidate at the Institute of Arctic and Alpine Research at the University of Colorado Boulder. And I just wanted to present a few slides to touch on some aspects that were discussed in the video. I'll try not to take too much time so that we can leave more time for questions at the end. And so I think the main focus of that video was what we call the Ice Albedo Feedback. Just as a reminder, if that wasn't clear, we define the albedo as the ratio of solar radiation that is reflected by a surface over the total incoming solar radiation. And what happens is that as air temperature rises, there's more snow and ice melt, and then that leads to more open ocean being exposed, and the open ocean has a lower albedo than ice and snow. And so that leads to an increase in absorbed sunlight, which then warms the surface ocean, and then the surface ocean can also warm the atmosphere after that. And so as you can see in the little picture here on the left, you can see how ice with snow is very reflective. It has an albedo of about 0.9. And so it reflects most of the sunlight, and not a lot of it gets to the ice or the ocean. Bare ice has an albedo that's a little lower, about 50%, and compared to open ocean, which absorbs almost all of the incoming solar radiation. And so I wanted to touch a little bit on Arctic amplification, which basically is over the past 30 years, the Arctic has warmed roughly twice or maybe even 3 times the rate as the entire globe. And the question is, why is that? And so what you can see on the right here is a map of the globe that is showing the temperature change from 1960 to 2019. And you can see that the warmest color, that kind of red-brown color, is centered over the Arctic, meaning the Arctic is the place on the globe that has warmed the fastest. You can also see this in the graph on the bottom, which is basically showing you the warming per latitude band. So at the complete left of the graph being the South Pole, in the middle being the equator, and on the right being the North Pole. And you can see how the warming is really amplified in the Northern Hemisphere, and especially in the Arctic. And so why is that? And there are multiple reasons why Arctic amplification is happening. The main reason that is cited is the loss of Arctic sea ice. And so what I'm showing you here on this graph on the left is the extent of Arctic sea ice throughout the year from January to December. And what you can see is that in the lighter shades of pink, those were in the past years, in the 1980s, for example, and in more recent years, so in the 2000s, those are in the darker pink shades. And you can see that the darker lines are always lower than, I went backward, than the lighter shades of pink, meaning that we've lost ice on average throughout the year during all the months of the year, but especially the difference is especially large at the end of the summer in September here. Another way to look at this is visually, so these maps. So this is an example of how much ice and the coverage that it had in September 1979, when we first started to have satellite observations in the Arctic. And as an example, this is September 2012, which is the year so far where we've had the lowest amount of sea ice coverage. And you can see how different these two pictures are looking. And so what this does, when you look at it, it's white compared to well, blue in this color, but the ocean is actually pretty dark. And this affects directly the ice albedo feedback that we've talked about. You can see that all these regions that were right before would have been reflecting solar radiation, and now they are the ocean over these regions is absorbing solar radiation and contributing to this Arctic amplification. So just to put this into context, like how much coverage is that, does that represent? We've actually lost, over the period of satellite observations, we've lost about 3.5 million kilometers square of ice in the summer. And that area is about the size of all these red states. If you compare with areas in the US, I live in the US right now, so that's an easy comparison for me. But what is most alarming is if we were to lose all of the sea ice, it would represent losing an area that is the size of all of the contiguous United States. And so that is a really large area, and that means a lot of solar radiation gets absorbed by the ocean, whereas before it didn't. There are obviously a lot of other causes to Arctic amplification, and this is still an active area of research. Some of those include changes in atmospheric and oceanic heat transport, changes in the cloud cover and water vapor. Those two, I feel like the video about atmosphere climate feedbacks would explain that very well. Soot on snow and many more. I wanted to touch quickly about why you should care about Arctic sea ice loss, because I hear this question a lot. You know, we live in the mid-latitudes, we don't live in the Arctic. Why should I care about ice melting really far away from me? And one of the main reasons is that changes in the Arctic climate are really important because the Arctic kind of acts as the refrigerator for the rest of the world. It really helps to cool the planet. And so some of the reasons that I can name here are societal, ecosystem, economy, and security impact. You know, obviously a lot of species are affected by the loss of sea ice. A lot of populations that live in the Arctic are affected. There are also a lot of interest in economic development in the Arctic that could be more important in the future as the sea ice retreats. But I feel like what really affects us more personally is the weather and climate effects and feedback that the sea ice loss creates. And so as we melt more ice, all that fresh water goes into the ocean, and then with the global ocean circulation, that heat and that fresh water can be brought to lower latitude and change the ocean currents. But I think most importantly, it leads to more extreme events at lower latitudes. So things like flooding, drought, and fires. And the reason for that is because of another feedback loop, which is that when the Arctic warms, the temperature difference between the Arctic and the equator decreases. And because of that, the jet stream winds are slower and there is more meandering of that jet stream. And it's basically that meandering of the jet stream that leads to more extreme events at our latitudes. What this means is that we basically get stuck in weather patterns for longer. And if you get stuck in a weather pattern where it's raining, it's going to rain for a longer time. And so your risk of flood increases. But again, I feel like if you want more details about that, I would encourage you to watch part 4 on atmosphere of these feedback loop video series. And I just wanted to end with what my research focuses on. And so throughout my PhD studies, I've used global climate models to better understand the different processes that lead to Arctic sea ice loss over the 21st century in the context of forcing uncertainty and the internal variability of the climate system. So I'm just showing you here a figure in one of my papers where we've looked at on the top, the sea ice extent in the summer in September with time, and at the bottom in March. March is the month where we have the largest aerial coverage of sea ice. And this is for different climate models, included observations here in red. And you can see a lot of differences between these models. Some of the models, like the blue one, agrees really well with observations, whereas the orange one, not so much. Oh, I went too fast again. Okay. And another example is that these two orange and blue models, it seems like in the winter, they start to see a really drastic loss of Arctic sea ice towards the end of the 21st century, whereas this other gray model didn't show that. And so we're trying to understand the processes that can explain these differences so that basically our predictions of Arctic sea ice become more reliable. And so this is all I have, and I will stop sharing and happy to take any questions.
Thank you, merci Patricia. So I'll recommend that folks use the Q&A. I don't think we have any questions in yet. And then I'll suggest that we do the questions at the end of the presentation. And we have 2 more clips before Dr. Muma speaks. So we're going to show the permafrost and the forest ones. And we're not going to show the one that Patricia suggested, the atmosphere one. So recommend that everybody go home, and we're already all home. I don't know what I'm saying. Rita, when you're ready, we can watch the permafrost one, which is going to be short. Just heads up, everybody. It's just going to be the first 3 minutes. Okay.
In the northern hemisphere, nearly 1/4 of the land is covered by an icy expanse called permafrost. Extending from the surface down thousands of feet, its soil contains billions of tons of carbon-rich plant and animal remains suspended in a perpetually frozen state. But now, with human activity warming the Arctic 2 to 3 times faster than the rest of the globe, this permafrost is starting to thaw. And alarmingly, it contains twice as much carbon as in the atmosphere today, and 3 times as much as in all the world's forests combined. As it thaws, microscopic animals called microbes Earth is warming, caused by the burning of fossil fuels like oil, coal, and natural gas, filling the atmosphere with heat. Have been frozen for up to tens of thousands of years are waking up and feeding on the newly thawed carbon remains, emitting dangerous heat-trapping gases.
If we were to take all of the microbes on Earth, we'd find that they'd weigh probably 50 times more than all of the animals on Earth. Now, these microbes need to eat, and what they eat are the dead remains of plants and animals. And as a byproduct of feeding on that material, they produce carbon dioxide and methane.
To understand how warming temperatures accelerate microbial activity, you need to look no further than your own kitchen.
It's like having a chicken in your freezer. You take that chicken out, you put it on the counter, and it starts to thaw. And then you go away for the weekend, you forgot about the chicken that's on the counter, and you come back and, the house smells and the chicken's decomposed. That's what happens to the carbon that's in permafrost. It's fuel for microbes. As they're breaking it down and using that fuel, they're releasing greenhouse gases, carbon dioxide and methane into the atmosphere.
Driven by fossil fuel emissions raising the temperature in the Arctic, these microbes are amplifying the warming as the permafrost thaws by releasing more carbon dioxide and methane into the atmosphere and warming the climate even more in a self-perpetuating loop. Which of these heat-trapping gases is released depends on the environment in which microbes digest the carbon. In oxygen-rich conditions like soil and lake surfaces, microbes produce carbon dioxide as a byproduct. But in environments lacking oxygen, like bogs and muddy lake bottoms, they produce methane, which is nearly 30 times more potent at trapping heat than carbon dioxide. Scientists predict the impact of both methane and CO2 added to the atmosphere from permafrost thaw will be staggering.
The amount of carbon that could be released from thawing permafrost by the end of this century has been estimated to be up to 150 billion tons of carbon. So to put that in context, the US is currently the second largest greenhouse gas emitting country in the world. If we took our current US emissions and added that up through 2100, this is on par with the amount of carbon that might be released from thawing permafrost.
Last summer, while working in her usual field.
So that's it for the permafrost clip. We're going to go over to the forest clip as soon as Rita is ready. Thanks for being here, everybody. I know this isn't the most pleasant Thursday evening viewing. This is my 3rd time watching these, and I'm not enjoying it anymore. The 3rd time. Oh, here we go. Thank you.
20 years ago, I started photographing our oldest trees. They can be 4,000 years old. Some are dying from disease, insects, lack of rain, warming temperatures. Never did I realize that within my lifetime I would be recording their deaths.
It's really astonishing in a forest the extent to which the trees produce a canopy that is fairly uniform, fairly dense. They parcel out the space up there among themselves as though they had decided ahead of time, you get this space and I get this space. They don't really think of it that way, but that's the way it works out.
Trees are miraculous in other ways too. As they reach out with their leaves and branches, they play a vital role in the health of the planet. Through photosynthesis, they help regulate Earth's temperature by pulling carbon dioxide, a powerful heat-trapping gas, from the atmosphere and emitting oxygen. Since carbon dioxide warms the atmosphere, by removing it and storing much of the carbon safely away in their branches, trunks, leaves, roots, and soils, forests help cool the Earth. In fact, every year, terrestrial ecosystems remove about 30% of fossil fuel emissions, and forests are responsible for most of that. But that percentage is decreasing as emissions increase, steadily raising Earth's temperature and threatening forests' ability to offset the warming.
We have warmed the Earth by a full degree and a little more, and forests are suffering increased hazards of fire as they get warm and dry, increased hazards of disease as they become vulnerable to insects, and dying as a result.
As trees die, they become part of a dangerous feedback loop kicked off by the warming. As the temperature rises, the climate becomes hotter and drier, and they fall prey to drought, fire, and insects. With fewer trees left, more heat-trapping gas remains in the atmosphere, raising the temperature higher, resulting in even more dieback. As trees burn and decay, the carbon they've locked away during their lifetime, what scientists call a carbon sink, is released back into the air.
It's entirely possible we reach a point where we're killing off forests much more rapidly than carbon can be fixed by forests. The net result then is to produce a feedback that's lethal.
Today, we have a choice. Allow trees to do their job and cool the planet, or jeopardize the forests we have. That's the path we're on right now. How we protect and manage forests will play a large role in determining our future. When it comes to global warming, 3 major forests matter the most: the tropical, the boreal, and the temperate. No forest is more critical for cooling the planet than the Amazon. Spanning more than 2 million square miles across 9 countries, this tropical forest has been storing carbon for millennia. Yet it is dangerously close to releasing more carbon than it absorbs. Mike Coe is the director of the Tropics Program at the Woods Hole Research Center. For over 20 years, he's studied how deforestation in the Amazon rainforest affects the local climate and environment.
Tropical rainforests probably account for about 15 to 20% of all the terrestrial carbon sink, and the Amazon's half of that. So we're talking about a significant fraction of our annual emissions are being taken up by the Amazon forest.
But in the last 50 years, nearly 20% of this forest has been lost, mostly to slash and burn land clearing, triggering fires, insects, and tree dieback. This not only releases the carbon stored there, it jeopardizes an important cooling function of the Amazon rainforest. During transpiration, roots pull water out of the ground and release it as water vapor through tiny holes in the tree's leaves, creating a cooling effect on the surrounding air. In the Amazon, transpiration can cool the region by as much as 10 degrees Fahrenheit.
When we lose trees in the Amazon, when we cut them down, what we're doing is we're shutting off that transpiration. So what you get is a drier climate. And the more you deforest, the drier it gets.
Over the past 2 decades, the dry season has extended several weeks, stressing trees even more and creating an ideal environment for fires to spread.
During extreme droughts, a huge amount of the forest burns. That turns the forest that year from a net sink to a net source of carbon. And we can do the math. If that happens 5 times in a decade, this forest is now a source.
Today, tropical forests are absorbing 1/3 less carbon than they did in the 1990s. Scientists predict that with the loss of so many trees, the Amazon could flip to emitting more carbon than it stores as soon as the next decade.
You can imagine that the climate's changing a little bit and everything looks just fine, but then one day it changes just enough that the whole system flips over. You know, it's the classic frog in the water that you heat up. The frog's not noticing anything until it's way too late.
The next major forest at risk of tipping from a carbon sink to a carbon source is the boreal, encircling the North Pole through Siberia and North America. The largest forested region in the world, this vast coniferous expanse, stores an estimated 2/3 of all forest carbon, most of it locked away in frozen plant and animal remains deep in the ground. But that's changing. As with tropical forests, the warmer, drier climate here is making the trees more vulnerable to disease, insects, and fire. Brendan Rogers has been studying how boreal forests respond to climate change for the past decade.
Wildfires are getting worse across the boreal zone. We're seeing more and more large fire seasons, record-breaking fire seasons every year.
Unlike in tropical forests, the fires here strip off the insulating ground cover, preventing it from building up in between the frequent burns. Without this protective layer, fires reach further and further down, burning the organic matter stored in the soil.
About 75 to 90% of all the carbon stored in these forests is underground. And that is actually the majority of the carbon that's getting released from these fires.
The fires kick off a feedback loop, triggered by warming in the boreal zone. More fires burn carbon deeper down in the soil, releasing carbon dioxide and methane into the atmosphere, heat-trapping gases that make the climate hotter and drier, leading to more wildfires. Like the Amazon, the boreal forest is going to switch from a carbon sink to a carbon source. Scientists don't know exactly when, but predict that at the current rate, it will happen by the end of the century, crossing a tipping point that the forest can no longer recover from.
We're seeing rapid change now, so rapid that the system is essentially not used to it. And the scary thing is not knowing where that tipping point is.
The temperate forest makes up only 1/4 of the world's forests, but it's our best hope, since the tropical and boreal forests are on the brink of becoming emitters of carbon. Once cleared for agriculture, many temperate forests in the US and Europe have made a comeback in recent decades. But in the southeastern US, old forests are being cut down by the wood pellet industry for burning, releasing decades of stored carbon back into the air. Even though these forests are being replanted, when it comes to offsetting global warming, old and young forests are not equal. Beverly Law has been measuring the exchange of both carbon dioxide and water between our forests and our atmosphere for the last 25 years. She works at 2 long-term testing sites that are part of a global network of more than 500.
An older forest has a lot of carbon stored compared to a younger forest. In a young forest ecosystem, there aren't that many trees there, and they're not taking up much carbon from the atmosphere.
Old-growth forests in the Pacific Northwest store huge amounts of carbon. Not only are they thriving in the wetter and cooler climate, these forests will be less vulnerable to climate change over the next 30 years compared to other forests in the western U.S.
If I were to try and mitigate climate change, the best strategy is when you have forests that have low vulnerability to climate change in the future, and they store a lot of carbon already, is keep those forests like they are, preserve them.
But unfortunately, these hardy carbon-rich trees have been prized by loggers for centuries. Redwoods that once towered over the Pacific coast are now mostly gone. When a tree is logged, 1/2 to 2/3 of the carbon it stores is released through decay or burning of the unused branches, leaves, and roots, as well as from the surrounding soil. Today, 17% of global carbon emissions each year can be attributed to logging and burning wood pellets for bioenergy.
In Oregon, of all the forest that was harvested over the past 100 years, 65% of that carbon has gone back to the atmosphere. Now, this is just the wrong time for that in terms of climate.
The warming atmosphere poses another kind of threat. Unable to survive the higher temperatures, many forest species are migrating north to cooler climates. But not all species can do this, and it takes time, which is in short supply. With the clock ticking, it comes down to how we manage temperate forests. Use them for commercial purposes, or keep them intact to cool the planet. While human activity has kicked off natural warming loops, human ingenuity could reverse their direction, turning them into cooling feedbacks instead. It would mean protecting and expanding forests, preserving marshes, grasslands, and all natural habitats. Using agricultural practices that store carbon instead of releasing it, and letting trees and plants do their job of taking carbon out of the air. This would lower Earth's temperature and kick in a self-perpetuating cooling feedback loop. George Woodwell was an early pioneer warning about fossil fuel use, setting off warming feedback loops 5 decades ago. He's convinced the solution lies with nature's own ability to cool the planet.
We can store carbon in life. If we want to be optimistic, we have to be very progressive in our transition away from fossil fuels and into a new green world. But it takes imagination, interest, and a recognition of the reality of an Earth that is failing at the moment. We can't allow it to be too late.
Thank you, Rita. That's the end of all the videos that we had prepared. So we're going to move to our Q&A, which, we're going to let Dr. Muma speak, and then we'll move to the Q&A. So it's my absolute pleasure to welcome Dr. Muma. So grateful to have you with us.
Thank you. It's very nice to be here. And I want to share some things with you about the role of forests and what it might mean for addressing these problems, which are very real and very concerning. Let's see here. Let me just. All right. Forest solutions. Just to recap, you heard from Patricia that the combination of the loss of reflectivity of Arctic sea ice and the has led to the extra warming of the Arctic, and that extra warming has led to a more rapid release of methane from the land, and here it's showing it's even coming from the water. Sue Natali, who talked about the thawing chicken, has discovered in Siberia in particular, there are huge craters that have appeared in recent years that are methane explosions from under the frozen ground. So this is accelerating and very, very troubling. Let me just take you through a little bit of how the balance of carbon works in the system. This looks complicated, but I'm going to break it down so you can see what's happening. And it turns out that every year on average for the last decade, our fossil fuels there on the left, coal, oil, gas, have emitted 9.4 billion tons of carbon as carbon dioxide of the atmosphere. And that little orange arrow, 1.6, is, I think, an underestimate, but that's what's estimated to be the emissions that come from deforestation and land use changes, converting forests to urban uses and agriculture. So together, those add up to 11 billion tons. Now, the remarkable thing is, you'd think if we add 11 billion tons to the atmosphere, we would see an increase of 11 billion tons every year, but instead we see 5.1. So we put in 11 and we only see 5. Where does the rest go? Well, some of it goes there. The down green arrow is the absorption of vegetation by land. And the 2.5 the arrow going down is of 2.5 billion tons every year that goes into the oceans. So that's where it's going. Nature is already removing far more carbon dioxide than any technology we can imagine. As you heard, the forests alone are absorbing something in the neighborhood of 30% of what we put in every year. Tell me of one technology that is capable of removing anything like that. In fact, the attempts to do it so far is very close to zero. And yet we're spending significant amounts of money to develop those, and we're spending, actually giving subsidies to cut down the forests. And that's very troubling. And the feedbacks come when these, the waters and the land begin to warm up and release more of these gases back in the atmosphere, as you saw. That's what the red arrow is trying to indicate there. So we're adding more of the heat trapping gases as the Earth warms. Now, in 2018, the Intergovernmental Panel on Climate Change, I was not part of this particular study. I decided I'd done enough of these studies after 19 years. But anyway, this report came out at the request of governments, because in Paris in 2015, all the countries of the world, including the United States at the time, agreed that they would, that we should not allow temperatures to rise more than 1.5 degrees Celsius, or 2 degrees Celsius, and to make every attempt to keep it from rising more than 1.5 degrees. And so the governments asked the Intergovernmental Panel on Climate Change, which is an official United Nations organization that any country can belong to. And it has been tasked since 1989, when it was founded, with providing scientific and other information that governments can use to understand climate change and understand what to do about it. And so you heard Patricia's talk about computer models and so forth. There's so much complex things going on that that those can be put into with what we know about them, put into models to see what will happen. And so the scientists who do these reports took this task and said, okay, how do we keep the temperature from rising more than 1.5 degrees by 2100? That was the imperative put forth by the governments. And here's a direct quotation: to keep temperatures from rising excessively, global net anthropogenic carbon dioxide emissions must decline by about 45% from 2010 levels by 2030, Actually, I'm sorry, that's a typo. That should be 2005. I need to correct that. I'm sorry, I just noticed it right now. From 2005 levels by 2030, reaching net zero around 2050. Net zero means that we are natural systems are taking out as much as we are putting in. And so that's kind of, you hear all these all these statements being made by governments that, oh, we will be net zero carbon by 2050. Well, that's actually, I think, not very ambitious, because the current temperature rose in 2020 by about 1.25 degrees Celsius above the baseline years. And so we only have 1/4 degree to go before we are at 1.5 degrees if this continues at where we are right now. So the way to do this, though, they pointed out, is we must simultaneously reduce combustion emissions and increase removal of atmospheric carbon dioxide by additional forest growth and additional uptake of carbon dioxide on land. And it's not either or, it's both and. People will say, well, you can't do it all by growing forests. That's true, but you can't do it all by replacing coal with solar panels either. We have to do both together. And that point doesn't seem to have registered with most of the public, or they've just not been informed, but the policymakers who have don't seem to get the message. So how would we increase carbon accumulation by forests? And here is the photo is of a mixed stand forest in my part of the country, the Northeast United States, a temperate forest, which, as you heard, is our best hope because they are the least vulnerable to climate change compared to the boreal forests and the tropical forests. And you can see there's some little skinny trees and there's some big trees. And the idea is to let more of the skinny trees become big trees. And so there are several studies in recent years which suggest the possibility. A group in Germany, headed by Professor Erb, published a paper and which he concluded that if we altered forest management to let more trees grow, it would allow global forests to accumulate twice as much carbon as they currently hold. Now that's really extraordinary, because remember, the forests are already removing close to 30%, and that means they could be removing close to 60%. I can guarantee you that governments and the corporations and even the public will not allow that to happen. But any distance we can go towards that goal will be a huge help. The other stunning result that came out of another researcher by a researcher named Lutz and his colleagues, in fact, there are about 50 colleagues on that paper. They studied 48 forests in all parts of the world, tropical forests, boreal forests, and temperate forests. And they're finding, and this is a direct quotation from the paper, quote, the largest 1% of trees in mature and older forests comprised 50% of forest biomass worldwide. Biomass essentially means wood, and primarily is wood. And half the weight of wood is carbon. So if you double the amount of a tree, you've doubled the amount of carbon. So just take a look at this photo. You see a large tree on the right, and you see a bunch of smaller ones and a couple of middle-sized trees. And what this study says is that half of all the carbon on that plot is in the largest 1 out of 100 trees. Out of every 100 trees, one of them has, on average, half the carbon. So that means we need to let more of our trees grow to become big trees, because that's where the carbon is. And you heard Beverly Law talk about this as well, that these older forests store a lot more carbon than the younger ones. And I'll show you an example of that in a moment. And then a paper that just came out last September concluded that the potential for growing forests to accumulate carbon by natural regrowth is better than under active management. In other words, instead of, if a forest is cut down, letting it grow back naturally stores more carbon in the first 30 years of regrowth than does planting what you want to have grow there. And this is because forests are made up of different species. And when we replant, we usually replant the ones we want to cut down the next time. And nature plants the ones that are going to be thriving the most, and the mix of species the most. And so you get a better outcome. The other thing that they reported is that the potential for forests to store carbon has been underestimated by about 1/3, 32%. This is just showing a study that was done a few years back for a temperate forest here in New England, actually. It was in Vermont. And it shows, what is that, 10 different ways you can manage a forest. You can clear cut it on the left end, and you can do no management on the right end. And what you see is if you harvest it and turn it into wood products, and you often hear, well, we should harvest more forest and we can store the wood in wood products. Well, if you look at even with a clear cut, the light color compared to the dark color, only about half of the carbon gets stored in the wood products. And if you look at the total amount of carbon between what's left growing and what is in the wood products, and at the left end, and compare it to the bar on the right end, the total amount stored is sort of less than half of what is stored if you let the forest just keep growing. So this is a myth that is put out by economic interests that we should be cutting our forests and turning them into wood products and making more buildings out of wood and more products out of wood. But as Beverly Law said in her piece there, and I'm actually a co-author on that paper, but it's her measurements, that if you look at all the carbon that was in the forests of Oregon in the year 1900 when the forestry industry started, only 19% of it is in wood products today. And 65% of it is in the atmosphere as carbon dioxide, and 16% is in landfills. So we do not manage effectively and well. And there is a study that goes back to 1990, just showing the difference between how much carbon is in an old forest that is allowed to keep growing and one that is managed sustainably, meaning it's harvested every 60 years and allowed to grow back. And you can see the green bar at the top is the amount that was in the forest originally. And over time, this is on, I think, a 60-year harvest cycle, or maybe it's a 40-year harvest cycle, I guess. Yes, 40-year harvest cycle. And you can see that that after that old forest is cut, there's a big drop in the amount of carbon, and then there's a rise as the trees grow back, then it's cut again, and the rise, it goes back, and so on. And so the average amount in the forest over that 100-year period, I've drawn a red dotted line there. You can see here how much less carbon, if you look at the right-hand side, there is average in that forest than there is if it had been allowed to keep growing. And in looking at a managed 60-year rotation, you can see that in an old growth forest in the Pacific Northwest, the area that was shown in the film, it's way more than twice as much carbon is in an old growth forest than in one that's managed on a 60-year harvesting cycle. 611, I guess it's tons of carbon per hectare, and it's 274 for one that's harvested regularly. So when you hear that, well, we manage sustainably, which means we don't cut more than grows in a year, somewhere in the other part of the forest, that's not getting us anywhere. We have to do better than that. We have to be increasing the growth because that's increasing the removal from the atmosphere. So here's a picture of me in a forest here in New England, which has been, we've been cutting trees in New England for 400 years since the Pilgrims arrived in Pilgrim Rock, at Plymouth Rock in 1620. And yet here's an area where this tree right here is somewhere between 180 and 200 years old. It's a white pine. This particular tree holds about 4.5 tons of carbon. And that's the above ground carbon. It doesn't count what is in the roots. And that's a picture of me standing in this marvelous forest with these enormous trees. So planting trees is good, but letting them grow is better. And what we call letting them grow, we've given a name to, because we talk about reforestation when you replant or a forest that's been cut, or afforestation, you plant a forest somewhere where it hasn't been growing, but it was no word for letting forests grow. And so we came up with this term, proforestation management, published in a paper about 1.5 years ago. And it's caught on because forestation means to grow forest. Proforestation means you're in favor of growing forests. Seems fairly simple, but it's created a bit of a backlash among the people who want to cut forests. So proforestation management allows forests to reach their biological potential for carbon storage in trees and soils. And larger trees accumulate the most atmospheric carbon over time and store the carbon in the wood of their trunks and limbs and roots, I should have put. So it's the accumulation that's important. And so you can find times when there are trees that are younger than this one that are growing more rapidly, but if you cut down this one and plant those other ones, the new ones will never catch up to where this one was in having what it's removed from the atmosphere. It just, it's got to get as big as this again before it stores as much. Let me just give you an illustration of this. And this is based on actual data from a temperate forest in the Northeast. And it's the question about the cumulative carbon tons in an acre of trees in this region. And at 50 years, that acre holds 22 tons. And if you let it grow for another 50 years, it's 47 tons. That's the middle one. But if you cut it at 50 years and then let it grow back, by 100 years, you're back at 22 tons. And if you let it grow, it would be 47 tons. In other words, substantially more than twice as much. And if you repeat this another time and go ahead and let it grow, do this cycle for another 50 years, after 150 years, you're back to 22 tons. But if you had let it grow, it would be almost 76 tons. And so that's an important thing. And now you heard about the discussion about the bioenergy, where they're cutting forests to burn in place of coal, and they call it carbon neutral because in 50 years you're back to where you were at 22 tons per acre. And in fact, we would be far better off not to have burned that wood and allowed the trees to grow, to accumulate more carbon. So, just reducing the carbon dioxide here is what it's all about. And we do that by increasing that downward green arrow, the 3.4 billion tons a year. Now, what that will do is it will begin, as soon as we get to the point where we have reduced our emissions from everything we can, and we've increased the growth of forests and other systems, grasslands, wetlands, and so forth, then we will start removing carbon dioxide from the atmosphere. As we remove carbon dioxide from the atmosphere, the Earth will cool. As the Earth cools, these feedback loops will diminish, and they will diminish more rapidly the more we cool. So instead of increasing the amount of heat trapping gases as we do things, we will be decreasing them. So ironically, it's a situation where we can help protect protecting the Amazon or protecting forests in Nova Scotia or in Massachusetts will actually eventually help to refreeze the Arctic. It could get to that point. So we need to close this gap, this 5 billion ton a year gap, by preventing deforestation, the draining of wetlands and soil loss, restoring them And that's all essential to avoid irreversible and catastrophic climate change. And proforestation management is far more effective than planting 1 trillion trees, which you've probably heard of, and is among the least costly options for removing and storing additional atmospheric carbon dioxide. So let it grow. Thank you.
Thank you, Dr. Muma. I'm very in favor of what you're proposing, which I think makes me pro-forestation.
Good.
I'd like to welcome Patricia back and Anita. There we go. So it's 8:30 right now. We're scheduled to go to 8:40 for the questions. That's 10 minutes. We have 3 right now. Please, everybody, take this opportunity to ask any. I think this is a beautiful opportunity given the subject, because we have, 2 scientists with complementary interests that map exactly onto what we've seen, and we've got someone here who has been a professional during the whole course of this crisis, and another who is entering, beginning their scientific career, hopefully at the turning point. So I think this is a really great opportunity. And then I'll come back around 8:40 with closing remarks. Anita, the floor is yours.
Great. Thanks so much, you two. We do have a few questions. The first 2 are, just open it up. The first 2 are for Patricia, from a certain Sophie. Maybe you know her. Donc, je me demandais si le pôle sud sera également affecté par le feedback loop, et si oui, pourquoi?
Donc, c'est certain que le Ice Albedo Feedback, ça fonctionne aussi dans l'Antarctique. Je veux dire, si la glace fond, tu as le même principe que la radiation du soleil se fait absorber par l'océan. Le feedback est différent, ou plutôt son impact est différent dans l'Antarctique, et c'est toujours quelque chose qu'on ne comprend pas encore très bien. Mais il faut comprendre que la situation avec la glace dans l'Antarctique est différente de par le fait que la glace de mer entoure un glacier, tandis que dans l'Arctique, c'est le continent qui entoure l'océan où est-ce qu'il y a la glace. Donc, la géographie et aussi le fait que dans l'hémisphère sud, il y a beaucoup plus d'océans que de continents, tandis que dans l'hémisphère nord, c'est l'inverse. Donc, toutes ces choses font que les interactions entre la fonte de la glace et le reste du climat sont différentes. Mais oui, à la base, le principe du Ice Albedo Feedback fonctionne de la même manière. C'est juste que l'impact sur les autres composantes du système climatique vont être différentes.
D'accord, merci. Et encore une pour toi. D'après tes études, la glace de l'Arctique peut disparaître dans combien de temps si les habitudes mondiales ne sont pas changées?
Oui, donc en fait, ça, c'est une très bonne question parce qu'il y a un papier dans lequel j'étais co-auteur qu'on a publié récemment qui démontre qu'avec la nouvelle génération de modèles climatiques qu'on a, donc les modèles les plus récents et les plus à la fine pointe, ce qu'on a démontré, c'est que l'Arctique va devenir sans glace à la fin de l'été, en septembre. Les années, ça varie entre 2025 et 2060. Il y a beaucoup d'incertitudes parce qu'il y a beaucoup d'incertitudes dans le système climatique qui est un système très chaotique. Mais maintenant, on ne parle plus de vers la fin du centenaire, on parle plus vers le milieu du centenaire. Ce qui est un peu alarmant qu'on a découvert dans ce papier dont je vous parle, c'est qu'on a découvert que peu importe la quantité d'émissions de gaz à effet de serre qu'on émet à partir d'aujourd'hui, ce fait que la glace va disparaître en Arctique en milieu du centenaire va être quand même vrai. Et c'est simplement parce que même si on arrêtait complètement d'émettre des gaz à effet de serre aujourd'hui, le système climatique, ça prend du temps à s'adapter et les gaz à effet de serre qui sont déjà dans l'atmosphère sont encore là et réchauffent quand même l'atmosphère. Donc, on a découvert qu'on est rendu au point en Arctique que même si on arrêtait complètement, ça ne va pas changer la date à laquelle on va atteindre un Arctique sans glace à la fin de l'été. Donc ça, c'était un résultat très alarmant qu'on a découvert récemment et qu'on a publié dans une revue scientifique.
OK, wow. Ouais, très alarmant, comme tu dis. So this one is for both of you. And there's sort of 2 here that link together a little bit, but so it's really challenging to think of what we might be able to do in our own lives to reverse these very complicated feedback loops. based on scientific evidence, do Dr. Mouma and soon to be Dr. de Repentigny think that individuals can start to make a difference in changing the warming climate?
Well, let me take a first crack at that, and then Patricia can chime in. I'm actually, the answer is yes. The choices we make a difference. I mean, after all, the cutting of forests is because we are buying goods that require the cutting of forests. One of the biggest losses of boreal forests is the making of disposable paper products. We are literally, you know, flushing 400-year-old boreal forests down the toilet because we use, that's what it's made from. Could be made from something else. Paper towels, disposable diapers, all of those things are simply just one pass through, and then they are put into a landfill where they decay into methane, which makes it even worse. So there are choices we can make. We can make choices in the way we live. I'm speaking to you today from a zero net energy home in right in on the border of Vermont. We have we've had temperatures of well below 0 Celsius, 20 below 0 Celsius this past week, and we have 40 centimeters of snow right now. And yet this house is comfortably warm. We don't burn anything, nothing. We don't burn anything to keep it warm. Basically, we extract the heat from the sun that's stored in the land and the soil around us. We bring that into the house. It's not really all that warm. It's about maybe 15 degrees Celsius, which is warmer than the outside. And we have a heat pump that then raises the temperature up to a comfortable 20 to 25 Celsius temperature. And so it's possible to do. We did this 15 years ago. The technology is a lot better today than it was then. And it's much less expensive now than it was then. And we do it all with solar panels in a climate where right now they're covered with snow. So I'm having to draw from other renewable energy sources from the grid. But over the year, my house puts out more electricity into the grid than I use. And so, you know, it's doable. And then we do have to get away from the internal combustion engine in automobiles and vehicles. And the electric vehicles are here. The price is now in the mid-range of what the price of all vehicles are. So we can't complain they're too expensive. And if we do that, here's another little interesting compliment that comes with that. It turns out that the third largest warming gas is the ozone pollution that we get when we burn from our vehicle engines. And so if we get rid of those engines, we get rid of the tropospheric ozone, the air pollution. And the amazing thing about ozone is when you stop making it, it disappears within hours to days. So that's a really fast way of getting rid of things. So it's determined only by the rate at which we adopt non-combustible engines, non-burning engines. So there are a lot of things that we can do. Diet's another thing, of course. But it requires informing ourselves and then making decisions. What am I going to do to make a difference? And that will change the markets when we all do it, as we get enough of us doing it. So I think yes, individuals have a lot to do. And of course, as was said in the video, let's vote for political leaders who will make the changes. I think we've just done that in the United States. I'm hopeful compared to where we were. So there, a lot of individuals voted. That made a difference.
Thank you. So kind of relating, I guess, but sort of maybe a good segue actually with your last comment there. What do you suggest needs to be done to overcome corporate interests and persuade governments of the urgency with which we must act? So in other words, if one were to give a succinct message to our political leaders regarding climate feedback loops, to stop them in their tracks, what would you suggest?
Well, I think we should tell the political leaders to stop defending the polluting industries. Now, maybe it's a delicate U.S.-Canadian international issue, but the fact that in 1 week after becoming president, President Biden canceled the Keystone Pipeline that would bring Canadian tar sand oil to Texas for refining. That makes a big difference. I know it made a lot of people in Alberta unhappy, but it really makes it much better for the climate. And that's going to be a stranded asset anyway, because we're going to move out of fossil fuel powered vehicles very quickly, I believe.
Mm-hmm.
I mean, the electric vehicles are so much superior, and as the price comes down, this is what people who need a vehicle will buy. So it would have been a waste of resources to put it into a huge pipe like that has to operate for 50 years. But if there's no demand 20 years from now, what was the point? So yes, I think that's it. A number of corporations are actually beginning to do some very impressive things to reduce their emissions. There are now 270 major corporations that have said they will get all of their electricity from wind and solar power, basically. And some of them have already accomplished that. And these are really big companies. So as customers, let's let them know that we like that. Encourage them to do more.
Mm-hmm. Yeah, thank you so much. So we have one last question here for you, Dr. Muma. How do you think pro-forestation might gain currency as a strategy? You say that your paper has garnered a lot of interest. Maybe you can tell us a little bit more about kind of how to push that forward.
Well, it's been viewed online over 40,000 times, which is remarkable. I've never had a paper that's been viewed 40,000 times. As Patricia can tell you, we feel fortunate if 10 people read our papers, right? It's great. And that includes mom, right? I mean, there are just certain people who have to read it. I've been working with people with the European Commission they've been very interested in this, and working at the state level with some of the more progressive states, California and so on. It's too early to tell in terms of we have a new administration in Washington, but hopefully we can convince them that constantly subsidizing, as we do in this country, the cutting of our forests, and as there are fewer and fewer large trees left, there's pressure to cut even more of them. And the Forest Service, last figure I saw, in the United States, fewer than 7% of our forests are more than 100 years old. I mean, a 100-year-old forest is not a very old forest as forests go, because the trees in those forests can live to be 200, 300, 400 years. So they're cut, we're taking the children or maybe the young adolescents and not letting them grow to their full potential. So we really need to make that clear. And there are a lot of forest landowners who don't want to cut their forests, but the time comes, in the US at least, there's a big medical bill. There's a child who's going off to university. They need the money. Well, suppose they got a regular payment to keep it standing. And places where that's been tried, it's very successful. And you don't have to pay a lot to do that, to make the difference between a one-time, I'm going to get $10,000 or $20,000 for cutting this one time, and not in my lifetime will it be worth cutting again. Or I get a much smaller payment every month that just keeps me going and keeps the family, it makes the return on the investment in my land worthwhile. And so governments should, on government land, by the way, I was in Nova Scotia a year and a half ago, and I'd been there 50 years before, and I was really shocked at how much forest had been cut in that time. As I am every place I go in the United States as well, just how much more forest is cut than the last time I was there decades before. So we could change all that. And then these younger forests would be growing and really absorbing a lot of carbon.
Thank you so much.
Thank you both. Those presentations were wonderful. I thought they really complemented the video, and the questions and the responses were great. Just some closing remarks to folks. We can make a difference. It's a bit of a discouraging series of videos, but I take heart both in the recommendations that Dr. Muma and Patricia are making, and also in the actions that we do as a collective. So you're welcome to get involved with us or any other climate justice organization. I mean, it's all the same fight, and we're stronger together. So you can email us, lapechecgnd@gmail.com, and you can find us on Facebook at La Pêche Coalition. Green New Deal. If you're looking for something to do today, if you're feeling really amped after this event, we have been working on taking action on Bill C-12. So you can head over to our MP is not taking too much action in the Pontiac region, so we've been putting pressure on other MPs in collaboration with Lead Now. Lead Now has a little tool that you can use to email the key decision makers. Bill C-12 is a Climate Accountability Act for Canada, so we're hoping to see some action on that. It could be a really meaningful shift for us to maybe bring us in line with where the states are now, I guess. So merci. Merci à